This video is sponsored by Brilliant. Imagine a world where every fence post crumbles in a single rainy season, where decks sag into mush, and where laser is just a sci-fi word because lasers were never invented. No barcode scanners, no precision eye surgeries, no fiber optic backbones, just a big technology hole. Now imagine the fix for both problems hiding in a brittle gray metal: chromium. This is the element that lets wood shrug off rot for decades, that slips into rubies to ignite the first laser, and that keeps stainless steel from rusting in your kitchen. In this video we will explore where chromium came from, why its name means color, how its strange properties work, where we found it, and how we make it, and the many ways that it changed our world. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll, as we will be doing an experimental deep dive into one of the elements we've already talked about. Now in this cube we can see chromium in its pure form. Chromium is a steely gray metal with a high polish. It's hard and tough. In fact, it's one of the hardest elemental metals. On the Mohs scale of hardness, pure chromium metal is around 8.5, which is exceptionally hard. Now to put this into perspective, it's much harder than pure iron or copper. However, this hardness comes with a downside. Chromium is also quite brittle. If you had a bar of pure chromium metal and struck it with a hammer, it could crack or shatter rather than bend. This brittleness means pure chromium isn't used to make tools or structures by itself. They would be prone to snapping. Instead, chromium usually finds use combined with other metals, where its hardness and other traits can be best utilized. But enough about how it looks. You want to know, can you lick it? Now when it comes to metallic chromium, and that is what we talk about here in the periodic licking table, the shiny gray stuff in its pure form, it's relatively stable and doesn't just dissolve into your body if you touch it. So technically, a perfect clean piece of solid chromium wouldn't poison you if you licked it once. Now the real danger lies in chromium compounds, especially the hexavalent kind, which are toxic and definitely not something you want anywhere near your mouth. But even with the pure metal, it's not worth the risk. If you want chromium in a safe way, the good news is that your body can get tiny amounts of the beneficial form chromium-3 naturally from food. In fact, one of the richest everyday sources is vegetables like broccoli. So if you're craving chromium, it's much better to just eat your broccoli. Now, chromium's story begins in the 18th century. In 1761, a mineralist in Siberia discovered an unusual orange-red mineral, which he called Siberian red lead. This bright mineral, known as crocoite, owed its striking color to an unknown element. In the 1790s, when French chemist Louis-Nicolas Vauquelin obtained samples of this red lead ore, Vauquelin was intrigued by the mineral's color and decided to investigate it. In 1797, he succeeded in isolating a new metal element from the ore, the element we now know as chromium. He is credited with the discovery of chromium, becoming the first to obtain the metal by heating the ore in a charcoal oven. Upon discovering chromium, Vauquelin also noticed its presence in precious gemstones. He found that rubies contained a small amount of chromium, which was responsible for their red color, and the same element gave emeralds their lush green hue. This connection reinforced the idea that chromium was all about color, fitting perfectly with the name that it would be given. Now, throughout the 1800s, chromium found its way into practical use, mainly through its colorful compounds. One of its early uses was as a pigment in paints. That Siberian red lead chromate, became a popular pigment for bright yellows and reds in paint and dyes. Now, by the early 19th century, demand for chromium pigments was growing. In 1827, a large deposit of chromite, a chromium-rich ore, was discovered near Baltimore, USA. This provided a rich supply of chromium for industry. For a time, the United States became a leading source of chromium compounds, until even larger ore deposits were later found in places like Turkey in the mid-19th century. Now, chromium's role expanded as technology progressed. In the mid-1800s, chemists developed a process to use chromium salts in leather tanning, which soon became a widespread method to make leather more durable and flexible. By the end of the 19th century, compounds of chromium were being used to tan leather, replacing older vegetable-based methods. A tradition that continues today, with chromium being essential in most leather production. Another milestone was chromium's contribution to metallurgy. In the 1850s and beyond, experimenters realized that adding chromium to steel could make the steel much more resistant to rust. This idea culminated in the early 20th century with the invention of stainless steel. In 1913, British metallurgist Harry Brearley famously created the first true stainless steel by adding about 12% chromium to ordinary steel. The chromium formed a protective oxide layer on the iron, preventing it from rusting, and ushered in a new era of rust-resistant metals. Today, stainless steel, which owes its stainless quality to chromium, is everywhere. In appliances, utensils, tools, and architectures, all thanks to that crucial dash of chromium. Now, chromium even has a curious footnote in ancient history. For a long time, people thought that ancient Chinese artisans may have used chromium plating on weapons. Bronze arrowheads and swords from the Qin dynasty over 2,000 years ago were found in a remarkably good condition, and early analysis found traces of chromium on them. Now, this led to the theory that the Chinese had invented a form of chromium plating to protect metal from corrosion. However, modern research in 2019 revealed a different explanation. The chromium on those artifacts likely came from natural minerals in the lacquer used for coating the weapons, not an intentional plating technique. In other words, it was a coincidence of chemistry that preserved the bronze so well, rather than a secret ancient chromium technology. Still, it's fascinating that chromium showed up in artifacts long before it was formally discovered. Now, by the 20th century, chromium has gone from a lab curiosity to an essential industrial material. The stage was set for chromium to shine, literally, in the modern world. From a gleam of chrome-plated car parts to critical roles in alloys and even in pioneering scientific inventions. So what's in the name? In the case of chromium, the name itself hints at one of its defining traits. The word chromium comes from the Greek chroma, meaning color. This name was chosen because compounds of chromium can be brilliantly colored. Now, early chemists noticed that when chromium forms different compounds, they often show vivid hues: reds, yellows, greens, and purples. For example, one chromium compound called lead chromate is a bright yellow pigment that was once used to paint school buses. Another chromium oxide is a rich green color used in paints and glass. Even in nature, a tiny bit of chromium can tint minerals with intense shades. The red color of natural rubies and the green color of emeralds are both caused by a dash of chromium. Now, we've already established that in its pure form chromium is steely gray and that it's really hard, so let's move on to the other properties. One of chromium's standout properties is its brilliant lustrous surface. When polished, chromium reflects light with a mirror-like shine. We often see this in the form of chrome plating on objects. That shiny coating on car bumpers, wheel rims, or bathroom faucets is actually a thin layer of chromium. Chromium's reflectivity and luster make it appear very shiny. However, chromium is not actually the shiniest metal out there. In fact, if we measure reflectivity, silver is the most reflective common metal. It reflects more light across the visible spectrum than any other metal. But silver has its own issues. It's soft and it tarnishes quickly. Think of old silverware that turns dark. Chromium, while slightly less reflective than silver, has a huge advantage of being much harder and forming a protective surface film that resists tarnish. So a thin chromium coating stays bright and shiny for a long time without polishing. This is why chromium became the metal of choice for giving products a shiny, durable finish, even if it's not the absolute top of reflectivity. In essence, chromium is shiny enough and far more practical than a metal like silver for coatings. Other metals like platinum or rhodium are also shiny and non-tarnishing, but they're expensive. Chromium hits the sweet spot of performance and cost. This combination of high shine and corrosion resistance has made chrome synonymous with a flashy, long-lasting gleam. Chemically, chromium is a transition metal, and it's known for having multiple oxide states, meaning it can form ions with different charges and thus different types of compounds. The two most common oxidation states for chromium are +3 and +6, often referred to as trivalent chromium, Cr3, and hexavalent chromium, Cr6. Now, these different forms have very different properties. Chromium-3 compounds are usually stable and many are green or violet in color. For example, chromium-3 oxide is a dark green solid. Chromium-3 is also the form that is found in traces in our food and sometimes touted as a dietary supplement, though its nutritional necessities for humans is still debatable. Now, chromium-6 compounds, on the other hand, tend to be yellow, orange, or red, like potassium dichromate, a bright orange compound. Chromium-6 is a strong oxidizing agent, but it also is highly toxic and considered a carcinogen. The villain in the movie Erin Brockovich, the pollutant contaminating groundwater, was a hexavalent chromium compound. So while chromium metal itself is relatively safe to handle, it's bound up in solid form, some of its chemical compounds need careful handling due to toxicity. Now, one remarkable property of chromium is similar to aluminum. It is its resistance to corrosion. Chromium doesn't rust in the same way that iron does. This is because chromium undergoes passivation when exposed to oxygen. It forms a very thin, invisible layer of chromium oxide on its surface. Now, when you use this is the reason why chromium-plated objects stay bright. The thin coating of chromium quickly forms a oxide skin that prevents any further dulling or corrosion. Now, in terms of its physical properties, chromium has a fairly high melting point, about 1907 degrees Celsius or 3465 degrees Fahrenheit, which means it stays solid at very high temperatures. It also has a high density. Though it not as heavy as lead, chromium is about 7.2 grams per cubic centimeter, somewhat lighter than iron. Now, interestingly, chromium is the only elemental solid that shows entoferromagnetic ordering at room temperature. This is a type of magnetism where adjacent atoms' magnetic moments align opposite to each other, canceling out overall magnetism. In everyday terms, pure chromium is not strongly magnetic like iron. Any magnetism in chromium metal is a more subtle effect due to its crystallized structure. Now, chromium may not be as well known as iron or copper, but it is not particularly rare in the Earth's crust. It is estimated to be the 21st most abundant element in the crust, with an average concentration of around 100 parts per million. You won't find chromium as a native metal nuggets. It's too reactive to exist in pure form in the ground, but rather in minerals and ores. The primary ore of chromium is called chromite, which is an iron chromium oxide mineral with the following formula. Chromite typically appears as a dark, dense, rock-like material often found in layered igneous rocks that originated from cooling magma deep within the earth. Significant chromite deposits are found in various parts of the world. Historically, chromite was mined in places like the Ural Mountains in Russia and in Turkey, which was a major supplier in the 19th century. In the 21st century, South Africa holds the title for the largest chromite reserves and is the biggest producer of chromium ore by far. South Africa's Bushveld complex is famous for its vast chromium and platinum deposits. Other leading producers of chromite include Turkey, India, and Kazakhstan, which has large reserves as well. Countries like Finland, Zimbabwe, and the Philippines also have notable chromite mines. Essentially, chromium resources are concentrated in a few geological areas, and global supply depends a lot on mining in those regions. If you were to pick up a piece of chromite ore, it might not look too special. Typically, it's a dark brownish black rock, but that ore is the starting point for all the chromium metal and compounds we use. In nature, chromium can also be found in small quantities in other mineral. For instance, the mineral crocoid, lead chromate, we mentioned earlier, is a rare mineral that was important historically as a source of pigment. There's also a beautiful green mineral called uvarovite, which is a chromium-bearing garnet gemstone. Its emerald green color comes from chromium, but chromite remains the go-to mineral to obtain chromium in bulk. Now, to get usable chromium metal out of chromite ore, a series of steps is needed. You can't just melt ore and get chromium like you would melt iron from iron ore. The production of chromium is a bit more complex because chromite doesn't reduce to metal easily using common carbon-based methods, at least not to pure chromium. Here's a simplified overview of how chromium is typically produced. The majority of mined chromite is actually turned into an alloy called ferrochrome, rather than pure chromium at first. Ferrochrome is an alloy of iron and chromium, usually 50 to 70% chromium. The rest, iron, and a bit of carbon. To make ferrochrome, chromite ore is mixed with carbon, often coal or coke, and fed into a high-temperature electric arc furnace. At very high temperatures, the oxygen in the chromite binds with carbon, forming carbon monoxide or dioxide gas, and leaves behind molten ferrochrome. Essentially, the carbon acts as a chemical reducing agent, pulling oxygen away from the metal. The result is chunks of iron-chromium alloy. This ferrochrome can be used directly in steel making. It's added to molten steel to introduce chromium into the steel. In cases where we want pure chromium metal, for example for certain high-performance alloys or plating uses, an extra refining step is done. One common method is the aluminothermic process, which is a type of thermite reaction. In this process, the chromite ore, or the ferrochrome, is first oxidized to form chromium oxide. This can be done by roasting the ore with air, lime, or soda ash, which turns the chromium into a form like sodium chromate, then further processed to chromium 3 oxide. And once you have chromium oxide, a green powder, you mix it with a powdered metal fuel like aluminum and ignite it. The aluminum powder reacts vigorously with the oxygen in the chromium oxide, essentially stealing the oxygen to form aluminum oxide and freeing the chromium metal. This reaction produces a lot of heat. It's similar to the reaction used to weld railroad tracks together. After it cools, you get relatively pure chromium metal as one of the products, which can be collected. Now this is the reaction. Now this aluminothermic process is useful because it doesn't require electricity, just a chemical mixture and ignition. But it's usually done on a moderate scale for producing metal for specific purposes. Now, another way to obtain pure chromium is through electrolysis or chemical leaching methods. In one process, chromite is first processed into chromium salt, like sodium dichromate, then reduced chemically to chromium 3 oxide, and finally electrolyzed or reduced with aluminum as above. The key point is that producing pure chromium requires removing the iron and other impurities, which involves converting chromium into a soluble form and then back into a metal. Now, after reduction, chromium metal might be melted and purified further, for example by electron beam melting or vacuum arc refining, to remove any remaining impurities and to cast it into ingots, bars, or powder. Pure chromium metal often shows up as small crystals or metal chunks that are silvery. However, as noted earlier, pure chromium isn't often seen by end consumers. Most chromium goes directly into alloys or plating processes rather than being sold as pure metal pieces. One of chromium's most important roles is in metallurgy, the science of mixing metals to make alloys. When chromium is added to another metal, it often improves their strength, hardness, and resistance to wear and corrosion. The prime example of this is steel. Now, regular carbon steel, iron with a little bit of carbon, is strong, but it rusts readily when exposed to water and air. However, if you add about 10 to 12% chromium to steel, you get stainless steel, which, as the name suggests, is far more resistant to staining or rusting. The chromium in the alloy forms that invisible protective oxide layer on the surface, preventing rust. Now, this discovery changed our world. Suddenly we had steel that could be used in damp kitchens and hospitals, in marine environments, and for the architectural facades without corroding away. Now, when most people hear chrome, they might think of a shiny chrome-plated car parts or motorcycle with gleaming chrome accents. Chromium plating is another huge application of this element, transforming ordinary metals or plastic into objects with a bright mirror-like surface. The process of chrome plating involves electroplating. An object is dipped into a solution containing chromium compounds, usually chromic acid or another chromium-6 solution, and an electric current is used to deposit a thin layer of metallic chromium onto the object's surface. The result is a coating typically only a few micrometers thick, very thin, but enough to completely change the appearance and surface properties. Now, why plate things with chromium? Well, for two main reasons: appearance and protection. Aesthetically, chrome plating gives a brilliant silver shine that doesn't easily dull. It's interesting to note there are two types of chrome plating. Generally decorative chrome, which is the shiny thin layer, often applied on the top of nickel plating to give extra smoothness and luster, and hard chrome or industrial chrome, which is a thicker layer of chromium used not for the looks but for the wear resistance. For example, hydraulic piston rods or engine cylinder liners might have a thicker chrome coating to reduce friction and wear. In both cases, chromium's hardness and stability are key. Now, one downside of the traditional chrome plating process is that it uses toxic chromium-6 chemicals in the plating bath. Workers have to be careful to avoid inhaling fumes or getting in contact with the solution, and waste treatment is needed for the leftover solution because hexavalent chromium is hazardous. In recent years, there has been a push to develop painting processes that use the safer chromium-3 compounds or other alternatives. In some places, regulations limit the use of hexavalent chrome in manufacturing due to environmental and health concerns. Despite these issues, chrome plating is still widely used, though manufacturers take precautions to manage the risks. Now, given that chromium's name comes from color, it's no surprise that many of its compounds have found use as pigments and dyes. In fact, some of the most famous traditional pigments in art and industry were chromium-based. One of the earliest was chrome yellow, which is lead chromate. This bright yellow pigment was adopted in the early 19th century for paints. Artists loved it for its vibrant hue, and it was also used in commercial paints. In the United States, school buses were famously painted in a color known as National School Bus Chrome, a warm yellow derived from a mix of pigments that included chrome yellow. Now, this pigment had excellent covering power and brightness. However, it had a downside. Exposure to air and light could darken it over a long time. It would form some green chromium-3 oxide on the surface, and more importantly, it contained lead and hexavalent chromium, both toxic. Over the years, due to environmental and health regulations, chrome yellow was phased out of most applications and replaced by organic pigments or other safer inorganic pigments. If you see older paintings or signs with a strong yellow, there is a chance they used chrome yellow, but modern ones use different formulations. Another pigment is chrome green, which can refer to a mixture of chrome yellow and Prussian blue to get green, or to chromium-3 oxide itself, which is a stable green pigment. Chromium-3 oxide is extremely durable and light fast. It doesn't fade in sunlight and it's chemically very stable, since it's basically the same oxide that protects stainless steel. It's used in green paints for applications where longevity is needed, and even a fine powder for polishing. Jeweller's Rouge has a variant that's green, called chrome oxide green, used to polish metals. Chromium oxides have also been important in the glass and ceramics industry. Adding a small amount of chromium oxide to glass yields a rich green-colored glass, often seen in wine bottles or old glassware. That deep emerald green is often from chromium. In glazes for ceramics, chromium can produce green colors as well, valued in pottery. There is also a red pigment based on chromium. For example, chrome red is essentially lead chromate combined with lead hydroxide, a variant of chrome yellow chemistry that gives a redder tone. It is worth noting that because of their toxicity, many chrome-6 based pigments have been replaced in modern use. Zinc chromate, a yellow anti-corrosion pigment once used in military to avoid primers, has largely been replaced by safer alternatives like zinc phosphate. Now, still, the legacy of chromium in the world of color is significant. For a long time, if you wanted the brightest yellows and durable greens, chromium was the go-to element providing that color. And let's not forget nature's own use of chromium for color, as mentioned. Gemstones. A tiny impurity of chromium in the mineral corundum, aluminum oxide, yields a ruby. Remove that chromium and the corundum is just a sapphire. If it has other impurities like iron or titanium, it can be blue. If pure, it's colorless. In emerald, which is a form of beryl, beryllium aluminum Silicate, a small amount of chromium substituting for aluminum, gives the crystal its green color. These gems have been treasured for centuries, and it's interesting twist that the same element used to make industrial yellows and greens also paints the beauty of rubies and emeralds. Chromium doesn't only preserve metals from rusting, it can also preserve organic materials like wood and leather from decay. If you've ever built a deck or bought a pressure-treated lumber for outdoor use, you might have encountered wood with greenish tint. For many decades, that greenish wood was treated with the preservative called CCA, which stands for chromated copper arsenate. CCA is a mixture of compounds containing chromium, copper, and arsenic. The chromium in CCA, in the form of hexavalent chromium compounds like chromic oxide, plays a crucial role. It helps the preservative chemicals bind to the wood fibers and prevents rot by poisoning fungi and insects that would otherwise eat away the wood. The idea here is that if you never want your wood to rot, you infuse it with a chromium-based preservative under high pressure so it soaks deep into the wood. The copper in the mix protects against fungi and pests. The arsenic is a powerful insecticide and fungicide, and the chromium acts both as a fungicide and as a fixer that locks the chemicals into the wood by reacting with the wood structure. The result is wood that can last for decades outdoors, even in contact with soil and moisture, without rotting or being destroyed by termites. Think of telephone poles, fence posts, deck boards. Many of these used to be treated with CCA to vastly prolong their life. CCA-treated wood was extremely common in the late 20th century for any construction where wood was needed to be long-lasting and low maintenance. However, because it contains arsenic and hexavalent chromium, both toxic, there were concerns about its safety. For instance, arsenic could leach out slowly and get into the soil or be a hazard if wood was burned. Moving from wood to leather. Chromium is also a superstar in preserving animal hides and turning them into leather. The majority of leather today, roughly 80 to 90%, is tanned using chromium salts, a process invented in the mid-19th century. Before chromium, leather tanning was done with plant extracts, vegetable tanning using tannings from bark, etc., which took weeks or months and produced a heavier leather. Chromium tanning, introduced around the 1850s, revolutionized the industry by significantly speeding up the process to just days and producing softer, more supple leather that was also stable and water resistant. The typical chemical used is chromium sulfate, often called chrome alum or just chrome. In the tanning process, animal hides are soaked in a solution of chromium salts. The chromium ions bond strongly to the collagen proteins in the hide, stabilizing them. In essence, the chromium cross-links the protein fibers so they won't decompose or putrefy. And it also gives the leather a bluish tint in the intermediate stages. Tanned hides are often called wet blue before they are dyed into other colors. The resulting leather is more resistant to water and heat damage than untanned hide, and it doesn't easily rot. Chromium tanned leather is used for everything from shoes and jackets to car upholstery and handbags. While chromium 3 used in tanning is much safer than chromium 6, there is still interest in reducing the environmental impact. Leather factories have to treat their wastewater to remove excess of chromium. In well-run operations, they even recycle the chromium baths. Some specialty leathers are chrome-free, tanned with other metals and vegetable tannings for those who want to avoid chromium entirely. But so far, chromium tanning remains dominant because it produces high-quality leather efficiently. Now, perhaps one of the most fascinating chapters in chromium's story is its role in the dawn of the laser age. Lasers are so common right now in scanners, pointers, medical devices, that it's easy to forget that the very first laser was only demonstrated in 1960. And it wouldn't have been possible without chromium. The first working laser was a ruby laser invented by Theodore H. Mayman. Why a ruby? Well, a ruby is essentially a crystal of aluminum oxide, sapphire, that contains a small amount of chromium. The chromium is what gives the ruby its red color. Now, Mayman used a synthetic ruby crystal with a few thousandths of a percent of chromium embedded in it. As the hard the gain medium of his laser. When he pumped this ruby rod with intense flashes of light from a photographer's flash lamp, the chromium atoms in the ruby absorbed energy and then released it as a burst of coherent red light, a laser beam. The choice of the ruby was inspired because chromium ions in the aluminum oxide lattice have energy levels that allow them to store energy and then emit it at a specific wavelength, about 694 nanometers, a deep red. When Mayman hit the ruby with a strong flash of white light, the chromium atoms, electrons, got excited, particularly by the green and blue wavelength in the flash. As those electrons relaxed back down, they emitted the red light. Now with mirrors at the ends of the ruby rod to bounce the light back and forth, the more chromium atoms were stimulated to emit light in unison. And suddenly you had a concentrated pulse of red laser light. This was the birth of the laser, a milestone in modern technology, and it happened with chromium at its core. Now, why chromium and not some other element? Well, it turns out that chromium in the ruby has a long-lived excited state, which is the key to achieving a population inversion, more atoms in an exciting state than in the ground state, a requirement for laser action. The specific properties of chromium in the crystal lattice of the sapphire were just right to make this possible with the technology at the time. After the ruby laser, other types of lasers were quickly developed using different materials and gases. But the ruby laser proved that lasers were feasible. While modern lasers often use different materials like neodymium in YAG or crystals for infrared lasers or various semiconductors for the lasers in DVD players and pointers, the legacy of that first laser remains a proud part of chromium's resume. If you ever get your hands on a synthetic ruby, or see a ruby laser on display in a museum, remember that without that chromium inside, it wouldn't be red, and it wouldn't have been a laser at all. Chromium literally helped light the way for the laser revolution. Beyond the big roles of alloys, plating, pigments, preservation, and lasers, chromium has a variety of other uses in technology and industry. It's a bit of a multi-talented element. In the mid to late 20th century, chromium found its way into the world of magnetic recording. Chromium 4 oxide is a magnetic compound that was used to make high-performance audio cassette tapes. If you remember the era of cassette tapes, you might recall some tapes labeled Chrome or CRO2. These were prized for the ability to store high-quality audio with lower noise compared to standard iron oxide tapes. Chromium dioxide's magnetic properties made it possible to record a wider range of frequencies, which meant better sounding music from a cassette. Though cassettes are now largely obsolete, for the time, chromium literally helped capture the sounds of the world. Similarly, some videotape formulations also use chromium-doped oxides. A fine powder of chromium oxide is used as a polish known as green rouge, for giving a final shine to knives, razors, and jewelry. If you see a jeweler polish a piece of gold or silver with something that looks like green chalk, it likely contains chromium oxide, as the abrasive that smooths the surface to a mirror finish. A mixture called chromic acid, made by mixing dichromate salt with sulfuric acid, was traditionally a cleaning solution for laboratory glassware. It's extremely good at oxidizing and destroying any organic residue, basically burning away any grease or grime on a molecular level. Chemists used it to ensure glassware was spotlessly clean. However, because chromic acid is highly toxic and corrosive, and the disposal creates toxic waste, most labs have phased it out in favor of other cleaners. Still, it's a testament to chromium's powerful oxidative properties. Now, talking about lasers and the physics behind chromium is a perfect reminder of how much our world runs on understanding science at a deeper level. Lasers work because of some very specific physics, electrons, energy levels, and light interacting in just the right way. It sounds complicated, but when you break it down step by step, the concepts are actually really approachable. And if you ever wish you could explore ideas like this, not just memorize facts, but really see how they connect, that's exactly what our sponsor Brilliant is all about. Brilliant is an interactive learning platform that teaches math, science, and computer science through problem solving. Instead of just reading about concepts like quantum states, magnetism, or math behind waves, Brilliant lets you play with them directly using interactive lessons and visuals. So if the story of Chromium sparking the very first laser has you curious about how physics actually works under the hood, Brilliant is a fascinating way to dive in. You can start with their course on physics fundamentals or go all the way into quantum mechanics and light. It's learning by doing and sticks so much better than just watching or reading. If you're excited about learning the world beyond just the elements and the periodic table, this is the perfect way to feed your curiosity. Don't let your brain get rusty. Galvanize your love of learning with Brilliant. To learn for free, go to brilliant.org on this link. Scan the QR code on screen or click on the link in the description. Brilliant's also given our viewers a 20% off on an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. From its colorful beginnings to its modern metallic shine, Chromium is an element of contrast and versatility. This silvery gray metal got its name from the Greek word of color, yet as a metal it's known for making things gleam. It was discovered in the reds and greens of rare minerals and is now mined by the millions of tons to form the steel skeleton of our cities. Chromium's special properties, its hardness, its resistance to corrosion, and its vibrant chemistry have made it a hidden keystone of technology. Now we would like to thank our members that support our channel. Thanks for doing this, we really appreciate you. Now if you think we missed anything, tell us in the comments, and if you want to know more about another element that is used in lasers, make sure to watch this episode about erbium next.